Okay, let's try this question. Here, they've given us the solubility product for calcium fluoride as 3.9 times 10 to the negative 11th. They'd like us to calculate the molar solubility of calcium fluoride in situation A, pure water, and situation B, a 0.20 molar solution of calcium nitrate. Well, when I look at those two situations, the first one, we're putting calcium fluoride just in plain old water, so nothing special there. But in situation B, we're adding a common ion into our problem. Both calcium fluoride and calcium nitrate have the calcium ion. Le Chatelier's principle predicts that if I boost the concentration of the calcium ion, I should have a shift to the left and less solubility overall. We should not get as much calcium fluoride to dissolve. Let's go ahead and prove that. Now, they've given us a KSP value. If we have a KSP, we need to write the chemical equation showing the dissolving process, and we need to write the KSP expression. I'm going to go ahead and do this for situation A. We've got calcium fluoride, CaF2, that is our solid. That solid is going to dissolve a little bit into calcium 2 plus ions and 2 F minus ions. I left off the symbol aqueous here. Now, the KSP expression for this, the KSP expression is going to be the concentration of the calcium ion here, Ca2 plus, multiplied by the concentration of the F minus, but we need to go ahead and square that event. Now, anytime we want to go ahead and solve for molar solubility, they're looking for X. Solubility product, SP, is our KSP. Solubility is the X term in our ICE table. So I know I'm going to need to make an ICE table. Initial, change, and equilibrium. Now, in our ICE table for situation A, they give me some solid here. How much? I don't know. It's not important. Now we're putting that solid in pure water. So in pure water, we don't have any initial calcium and we don't have any initial F minus. The solid is going to go ahead, dissociate a little to generate these two ions. How much calcium? Well, we're going to call that X. We're going to add X here, and we're going to add twice as much, 2X, to our fluoride. Now, at equilibrium, the calcium will be X and the fluoride will be 2X. Now we can plug all of those terms into our equilibrium expression. We know that the KSP value is 3.9 times 10 to the negative 11. That's going to equal the calcium, which is X, and the fluoride, which is 2X squared. 3.9 times 10 to the negative 11th will equal 2x squared is 4x squared times another x. That's going to be 4x cubed. Now, if you go ahead and solve for x, that's going to give us our molar solubility. We go ahead and get a solubility of 2.1 times 10 to the minus 4 molar. Okay, that's if we're in pure water. What about situation B, where instead of using pure water, we're going to use some calcium nitrate? We're going to do exactly the same process. We need to start with an equation. CaF2 as a solid, I'll call this situation B, dissolves a little bit into calcium ions and 2 F minus ions. The KSP expression is going to look exactly the same as well. Ca2 plus multiplied by F minus squared. The only difference is what's in our ICE table. We need to go ahead, do the initial, change, and equilibrium values. Now, initially, we have some calcium fluoride. I don't know how much, but I'm leaving it out. It's a solid. Initially, we normally have a 0, 0 here. When we're in pure water, both of those initial values are 0. However, this time we have one of those ions. One of these ions is in common to the solution that we went ahead and dissolved it in. Which one? The calcium. If we have a 0.20 molar solution of calcium nitrate, that's going to give us some calcium. All nitrates are super soluble. They're going to completely dissociate. This calcium nitrate will break apart into 1 calcium for every 1 calcium nitrate. So if we have 0.20 molar calcium nitrate, we have 0.20 molar calcium, but we don't have any fluoride. Calcium nitrite doesn't give us that. So those are the initial values. Since the fluoride is 0, we're going to have to go in the forward direction. We have to go ahead and produce some fluoride. You can't be at equilibrium if one of those are 0. So we're going to come over, we're going to add X to the calcium, but we're going to add 2X to the fluorides. Now at equilibrium, the fluoride will be 2X. 0 plus 2X is 2X. The calcium, on the other hand, the calcium, we're going to be able to rule of 100 this. It is 0.20 plus X, but since the equilibrium constant is incredibly small, 100 times K is less than my start, we're going to be able to ignore this X term, rule of 100 it, and simply call it 0.20. I'm going to use those two terms and plug them into my KSP expression. KSP is 3.9 times 10 to the negative 11th. That equals 0.20 times 2x squared. All right, let's go ahead and evaluate that. 3.9 times 10 to the negative 11th equals 2 squared is 4. 4 times 0.2 is 0.8. This is 0.80, and then we still have x squared. Now I'm going to go ahead and solve for x. If you go ahead on your calculator, evaluate what that is, you get 7.0 times 10 to the minus 6 molar. Now, if you compare those two solubilities, the solubility in water is greatly increased. This is a bigger number. We have greater solubility in pure water than we did when we had some calcium present. Again, Le Chatelier's principle predicts if we boost the calcium ion concentration, instead of being 0, we're now at 0.2, we should shift to the left over to the solid side, less solid will dissolve. I hope that helps. Take care.